Most interest rates in real life are not given to you on a term-by-term basis. Instead, they're quoted in terms of something called the annual percentage rate. You might have heard the three-letter acronym APR used when you watch car commercials or something like that. Now, the best way to learn what an APR is to take it from example. So, for example, credit cards are often quoted at about 24% APR compounded monthly. And this is a fairly realistic example. Now, there are two numbers that matter when you're trying to figure out what APR means. One is the rate, and the other is the compounding frequency. So in this case, our rate is 24%, and the frequency is monthly. What we're going to do in order to figure out the term rate is you're going to take the rate and you're going to divide it into equal chunks throughout the year. So in this case, because we're dividing monthly, we're going to take our 24% and we're going to divide it by 12 because there's 12 months in a year, and that gives us a term rate of 2% per month. So if I wanted to figure out how much money this actually cost me over the course of a single year, we could figure out what S12 is using our formula for simple compounding interest, and we would get, well, the usual thing. Like so. And again, right, the 12 in the exponent because there's 12 compounding periods in a year. Now, more generally, let's suppose we have a principal P compounding T times per year, and let's say that we're quoted an APR interest rate of R%. So after 1 year, we have this interest this value. And make sure that you understand why that T is in the exponent is because after 1 year, there have been T compounding periods because I'm compounding T times per year. All right, let's do an example. So let's suppose that we invest $100 and at a rate of 24%. Let's just use the same number that we had before. But let's look at it over different compounding periods. So let's say, yearly, semi-annually, quarterly, monthly, and let's even go down to daily. And daily does exist. There are things which compound daily. And notice that in each of these cases, it hasn't actually told you how many compounding periods there are in a year. It's up to you to figure that out. So for example, quarterly compounding periods means that it compounds 4 times a year. So I'm just going to go in and write out what T is in each of these cases, and hopefully nothing here is a surprise. All right, so let's start working it out. I'm going to build a table here to make it easy for us to read off the values. At this point, we're just plugging numbers into a formula, so there isn't a lot of work to do here. So I'm just going to fill out these numbers. You should feel free to double check these numbers and make sure that they look correct. Okay, so the table's now done. And let's see if we can see a couple of interesting things from this table. First of all, all the values are different, but more interestingly, the more often we compound, the more money seems to be made, right? So that's kind of an interesting thing which happens. The other thing to note is that the gaps are getting smaller, right? So the more often we compound, we are making more money, but the amount of money we make is very, very small. So for example, when we compound monthly, we make $126.82. And when we compound daily, we make $127.11. And that's only a difference of 29 cents, right? It's not really significant. But to see this even worse, let's say that we compound once every single second, right? So there's 31,557,600 seconds in a year. And if we do that, the value that we get, and you can check, is $127.12, which makes a difference of 1 cent. So a natural question is, well, if the gaps keep getting smaller, does this eventually stabilize? That is, let's say that we compounded every millisecond or every nanosecond or something like that. Does it get to a point where, sure, it makes more money, but the amount of money it makes is so insignificant that it doesn't make a difference? And the answer is yes. We will learn about something you can do called continuous compounding interest, where you compound it every single instance of time, and you actually get a meaningful number out of that. Not something that's like infinity. It actually stabilizes and gives you a meaningful number.